Hi, welcome. Thank you for showing up. I'm thrilled to be here. Many thanks to the organizers for inviting me. So you're probably asking yourselves, who is this guy? So my name is Luka Kladaric. I'm from Croatia. I am the chaos manager at Sakura Collective. It's an agency that I run. We deal with chaos. We don't do greenfield development. We won't build features for your site. We won't put buttons on your websites. We won't build your mobile apps. If you're drowning in tech debt, if you have performance or security issues, we'll put you on the right track and then hand off to an in-house team or a third party to do ongoing development. So I'm a recovering web developer of 10 plus years. These days, I'm mostly an architecture, infrastructure, and security consultant. I'm also a startup founder and a remote work evangelist. So before we get into the actual talk, what is the platform? What am I talking about here? So I'll be talking about the internal hosting platforms, the shared environment that all engineering teams use to host any kind of backend application, web or otherwise. So in 2017, I gave this talk called Zero-Downtime Data Center Failovers with a subtitle of Switching Hosting Providers for Dummies. I gave this talk at a bunch of conferences and meetups. It was basically a zero downtime migration between Rackspace and Amazon AWS and the tech stack that allowed us to execute this. This talk is kind of an update on what's happening with that stack, but you don't have to have seen that talk to understand what I'm talking about. And this is an update on the pain that we noticed over time and what we replaced that stack with. So the old stack, and I'll get into each of these so you don't have to know what they are right now. It's Ansible, Jenkins, HA Proxy, Nginx, and Isinga. So the first part, Ansible, was our config as code tech of choice. It allows you to declaratively describe the configuration of the servers that you need and which software you need installed and so on. We also abused it for deploying code. That's not what it was meant to do, but that's what we used it for, among other things. Jenkins was our CI/CD tool of choice, so continuous integration, continuous deployment. We were building artifacts with it and shipping them and the configurations associated with them using Ansible. We had a dedicated repository housing all of the jobs. Of course, config as code again. And we were using inheritance, meaning maximum coder use in the build and deploy jobs. So this was great if you were familiar with how it works. It was great for me because I was there when it was written. I contributed. But for a newbie, someone who had just recently joined the company or just switched teams to something that is deployed this way, it was impossibly complex to get into. We were using HA Proxy. It's a load balancing software. Of course, it was auto-configured from our Ansible, so just by the fact that an application exists, it also has load balancing configured automatically when we deploy load balancers. It's very powerful, very flexible. I love HA Proxy. Nginx, because we put multiple applications on a single box, we needed Nginx on that box to be able to route the traffic to the application that the request was meant for. So we had HA Proxy saying this request is meant for that box, but then when you get to the box, Nginx looks at it and is like, oh yeah, that's application A, and the next request is application B. It was one more thing to keep track of. It was mostly in the way. I don't remember one time when it did anything for us, except solve that one problem, but it's a full-fledged web server. We also used Isinga for our primary monitoring. Again, auto-configured from Ansible, mostly out of the way. It did its job with very little complaining. And, it was good. The entire thing did the job. The entire platform worked. It allowed us to pull off a very complex data center / provider failover without losing any requests by building an exact replica of what we had at Rackspace at AWS. So we spun up an exact copy of every single web server, every single database, everything, set up complex replication between them and so on. But ultimately what we ended up was a system that existed across two environments that were completely different, and it existed as a single organism. you could send a request to Rackspace and it would go, oh, that application has already moved to AWS. It would route through the site-to-site VPN the request to AWS, and then there the application would go, yes, that's me, but my database hasn't been migrated yet. So it would send the request back down the site-to-site VPN tunnel to get to the database. So not only was it good, it let us grow. We added applications to it with almost no trouble. Most of the applications were contained to a single file where we would say, we have this application, this is where the code is, this is the name of it that we refer to it by in the package manager, this is the web address where it should live, this is how many resources it needs to run, this is how you monitor it, this is how you, so on and so on. It also allowed us to scale out when we encountered performance issues that allowed us to add more machines that were configured exactly the same as the old machines and add additional capacity. It was very simple to do this, very simple to provision them and get more capacity added to the platform. We didn't really need more, with a team of just around a dozen engineers, we were doing about 100 requests per second. And when we were making this decision, what should we do? We went from 100 requests per second average to 2,000 requests per second at peak, but never dropping below 400. So we were 4x to 20x what we migrated with almost no investment in scaling. We added one more load balancer, but that was primarily because we wanted one more availability zone. That was it. So what broke? What actually made us do something? It wasn't the Python 3, it wasn't the Golang that really broke it. It was background workers. It was a perfectly reasonable request from the engineers of an existing Python application. I wrote background workers, I used them, I knew exactly what they were, but we didn't have anything like it in the current platform. And we spent way too much time trying to support it. It challenged almost every single assumption that we made building the platform. Up until that point, every single thing that we deploy and run was a web service. Background workers are not web. The health checks are different. Everything is different. So we figured out this platform had reached the end of the road. It became very apparent that we needed something new. So why did it die? Why could the platform not evolve? Because it was evolving fine until this point. It died because each thing had its own deploy pipeline. Because when you had a weird application, it wasn't just built weird. It was deployed weird, it was monitored weird, it was, subsequent deploys were also weird. And the complexity of a weird application stretched throughout the pipeline all the way to the end. So we were maintaining basically a bunch of pipelines in parallel, each acting differently. And that's, just a horror show. So what's the answer to this problem? Well, clearly it's containers. That's what everyone's talking about. It's clearly the way forward. With containers, you concentrate the complexity handling in the build stage. If you were at Valerie's talk, that's what she was talking about. The Docker file, it's everything you need. It describes everything that you need, and it's close to where the complexity originates, which is the source code. You put the Docker file next to the source code. The Docker file explains all of the weird shit that everyone did in the code base, and you end up with a container that is the exact same size as everything else, and that fits with everything else. So once you have an image, once you take the code base, apply the Docker file, you get an image. The deploy is exactly the same, regardless of what's inside the image. It's a container because it contains weirdness. Another thing that we wanted with a new platform was developer autonomy. When we started looking into this, we wanted to make it possible for teams to not just self-manage most. We wanted to reach a point where teams self-manage all of the infrastructure around their application, all of the how and the why, and have the infrastructure team just be there for support, for consultations on really stuff that is really out there, to be performance and security and so on, but not how do you ship an application. If you build a hello world, you should be able to get it in front of people without talking to my team. So how do I containers in 2019? I spent a few days trying to cram containers into our Ansible, Jenkins, HA proxy setup. And the more I looked at it, the more things I threw out and replaced with more natural fits. So the first to fall was Jenkins, and it was replaced with Travis. So Jenkins is self-hosted, means it's another thing that I have to, keep track of. But also, it's self-hosted. It's a box that we have to provision capacity for. So either it's bored, or it's over-provisioned and too expensive, or it's another thing that I have to manage scaling for. I have to worry about scaling for production. I don't want to manage scaling for tooling. Travis is a much better fit for a high-velocity engineering team because you just pay people and the problem disappears. You give them your code and you give them instructions how to build it, and they build it. I don't want my tooling to be broken because I don't have tools to fix the tools. I don't want tools to fix the tools. Travis file, to me, being YAML, is a lot easier to understand than a Jenkins file, which is what Valerie was showing on screen. Jenkins files are way better than what we used to do, but I just prefer Travis. And so building container images allows the teams to explain the complexities, like I said, of the code base locally and to fully control how their applications are built and deployed. Okay, so we built a container image that includes our application. What now? How do you run a container on the internet today? Kubernetes was already mentioned. I'm not an expert in Kubernetes. From what I know, it's a collection of software that makes it easy to start building massively distributed systems and very painful to maintain them in production. I dislike the kitchen sink approach. I dislike the fact that it is kind of modular, but as soon as you actually start using the modularity, you're on your own. There's no support from the community. And that eventually you figure out that you need the human resources to run a data center before you consider Kubernetes for production use. I may be 100% wrong. I welcome the conversation around this. Catch me in the hallways. If someone actually knows Kubernetes, I'm dying to talk to you. But yeah. So there's Kubernetes. There's a bunch of bad attempts at solving this problem that I will not even name. And then there's a whole lot of nothing. It's just empty space. And then there's Amazon ECS, Elastic Container Service. To me, it's like Kubernetes. If you read a high-level overview of what Kubernetes is and what it does, ECS is that, but it's built with AWS primitives. It's built with AWS components that already exist. So the services that we know and love, the services that we have been using for years. So you want load balancing, Amazon has a load balancer. It's called ELB, Elastic Load Balancer. You want DNS and service discovery, Route 53, their DNS service, et cetera, et cetera. So most of what Kubernetes does is not new. The new thing is running containers in a high availability way, running them around. But everything else is meta to the thing that it's supposed to do. And all of the meta things are new. With Amazon ECS, all of the meta things are things that I already use. Then there's Fargate. Fargate is, in my words, serverless ECS, whereas Kubernetes requires you to define your, an ECS classic requires you to define a cluster and the size of the node that it runs on. Of course, you can have auto-scaling, but that auto-scaling is in increments of nodes and so on. Fargate is, I want to run this image and I want to run 100 instances of it now, and it just does it. You say, I want 100 instances of this with half a gig of RAM, and it just goes and does it. There's no concept of where the boxes are running, where your containers are running. They're just running in the cloud. Of course, eventually it's on some server, but you don't care about the server. That's what's glorious about it. You don't know the configuration of it. You don't know the bandwidth of its drives, the memory consumption. You don't care about over-provisioning, under-provisioning, none of it. It's just stuff runs. So ECS, Fargate, right? I like the concept a lot, and I decided to go for it. Initial expeditions into it were painful. The console, the web console, supporting both classic/vanilla ECS and Fargate ECS is very, very, very confusing. There's so many things to click, so many values to enter. By the time you're through the console and you have something running, you've forgotten what the first thing you clicked was. I went through setting up an application on Fargate manually at least like 5 or 6 times. And every single time I was like, oh, I don't remember this. This is new. No, it wasn't. It's just such a long process. So how do we avoid clicking around the painfully confusing console? CloudFormation. So CloudFormation is infrastructure as code, something that we just at that point had to admit that we didn't have before. We had Ansible, which was config as code, but the actual boxes we still provisioned manually with various methods, but still it was manual. There's no record of how big each of the boxes are. So CloudFormation lets you declare what your infrastructure is supposed to look like in a unit called a stack. So you say, I need 3 machines. One's going to be the whatever, the other's going to be the app server, one's going to be the database, one's going to be the app server, one's going to be the Redis or whatever. And you can use native AWS services. You can provision EC2 boxes and run whatever you want on them, and so on and so on. It also lets us deploy the basic necessities. So like the subnets, the gateways, the firewall rules, the load balancers, the DNS zones to all of our AWS accounts. So we operate multiple Amazon accounts. Each is its own zone. One's production, one is dev, one is test, one is internal, one is whatever. And we have a unified network stack across all of them. So when you're deploying an application, you know that there's going to be a load balancer there called public load balancer. You don't have to provision your own load balancer or figure out where it is, how to configure it. You just know that a thing called public load balancer exists. So the individual applications expect to discover these resources within CloudFormation, because you can say there's a stack called the network stack, and within it, there's a load balancer called the public load balancer. And you don't have to have its unique ID. You don't have to have its IP, nothing. You just refer to it like that. And whichever account you deploy to you're going to get that account's load balancer. Simple reuse means the actual application templates are short and only contain the resources necessary for their operation, not everything else. CloudFormation console is where you can see who deployed what, which stacks are currently live. And it's basically the reason why it wins over Terraform, which is the first question I get whenever I mention CloudFormation, which is like, CloudFormation is terrible. Have you tried Terraform? I have not tried Terraform because I'm trying to build a system that hundreds of engineers can use to deploy their stuff. And I need a list of what was deployed. And CloudFormation does that. And CloudFormation is AWS specific. Terraform is cloud agnostic. It can provision on any provider. I explicitly don't care about that. We are explicitly all AWS. So despite the horrible YAML with functions but not variables or loops syntax, I still like it. It's still manageable. Isinga monitoring. CloudWatch wins on the fact that I don't have to run it, on the fact that it just exists, that Amazon takes care of it. I mean, Isinga wins. CloudWatch is inferior in terms of configurability, frequency, resolution, basically anything that you can think of, except for the fact that it just works, and doesn't need to be hosted, doesn't need to be nannied. It just works. Load balancers. I love HA proxy. If I could, I will figure out a way to use it. But realistically, we weren't really using any of its advanced features. And we were already using elastic load balancers to terminate the SSL traffic and distribute load between our HA proxies. And when we had things that we didn't want on the main production platform, we put them directly on ELBs. So ELBs are fine. I still need to figure out how to do logging in real time, but they're fine. So what's the actual implementation look like? By this point, you're like, yes, I've heard all of these things, but how did you actually implement it? There's a base networking stack. This is just things that individual applications will share. These are prerequisites. So you get the VPC, the main, like your private cloud network. Subnets, gateways, you need like public subnets, private subnets. You need internet gateways, you need NAT gateways, all of the networking stuff that nobody wants to think about. This thing solves for all engineers. You have a DNS zone, and the cool thing about this is because we deploy it to all AWS accounts, you get zone name dot internal company domain dot whatever. So you have prod.companyname.io, dev.companyname.io, and applications that want to live. So you have an application called foo. It just has to create a record called foo in the DNS zone. It doesn't care. The application being deployed doesn't care which zone it's being deployed to, which account it's being deployed to. Just because the DNS zone already exists, it has a prefix, you just say, hey, I am foo, and you exist, and you're reachable. Elastic load balancers, private and public. Public ones obviously take traffic from the internet. Private ones are only accessible from the internal network. The ECS cluster that will actually run those containers. The security groups of who can talk to what and so on. All of these are deployed from GitHub, where we host our code, via Travis to all our AWS accounts. So recently I needed to add something called the database group, or I don't know, something. I added it to the template, made a pull request. It provisioned that just to the dev account. I saw that it was good. I merged it. It deployed it to all of our accounts. Zero downtime, network level maintenance on our AWS accounts. And then once you have that, you can do the application CloudFormation stack. So what goes in the application CloudFormation stack? Something called a task definition, which is how you run one instance of a image, how you create one container. This has the definition of how much CPU this thing needs, how much RAM, which Amazon role it runs into, and so on. I have the service, where the service is like, I want that task definition to run at least 5 wide. I need 5 instances at any point in time. And then also, it can go up to this and so on and so on. So the CPU RAM spec and so on. You have the load balancer target group, which is just a thing that instances will automatically register to, so that the load balancer knows where to send the traffic. You have the listener rule that says, hey, if someone is looking for foo.zone.domain and so on, then that's me. Go to this target group. You have the log group. It automatically solves logging. Any application that is deployed gets a log group, and all of the logs from all of the instances of that application running are going to that log group. So you don't have to figure out where the logs are. You don't have to set anything up. Task roles and policies define which resources that application can access within Amazon, within AWS. So if your application needs an S3 bucket, it needs to be able to just read it. In that CloudFormation template, you say, okay, this application can access that S3 bucket and can read from it. And it can also access this S3 bucket and can write to it. In fact, if your application owns an S3 bucket, you can deploy that with the application. If it doesn't exist, it'll get created, and you can take the name and feed it as config into your application. So everything about the application is either in the code or in the Docker file or in the CloudFormation template. Or the Travis file, which actually, the Travis file explains the interaction between all of them. So application code is what your application does. Docker file is what it needs to do what it does. CloudFormation template is how that thing makes it onto some servers, and Travis file explains in which order, which things are run, and so on. So when you're starting out, when you join the company and someone tells you, okay, can you go and change some text on this application? You go like, where does that application live? And they tell you, it's this repository. You open it, and everything is there. And the README explains these 4 things and their the way they connect. And just by opening one repository, you can follow everything. So what does the CI/CD flow look like? You have GitHub push. So someone pushes some code onto some branch. You have Travis go, okay, some new code has arrived. We're going to build an image. It runs Docker build and so on. Once that's done, it pushes it up to ECR. That's the Elastic Container Repository. And then the next step is Travis deploy, which runs the CloudFormation stuff, which actually makes Amazon deploy your stuff to ECS. So what are the benefits of this? Like I said, all context and complexity about an app is in a single repo, compared to the old platform, which I loved until I figured out that if you wanted to deploy a new application, you had to define the application in Ansible. And then you had to add the DNS records and the DNS repo. And then you had to define the deploy pipeline in the Jenkins jobs repo. And then you had to manually deploy it to the servers because the first deploy is different from subsequent deploys, and so on and so on and so on. This, just by creating a repository, adding some code using our template for this Travis file, CloudFormation, all of that, just by it existing, Travis picks it up and starts building it. So you can legitimately fork an existing application, delete the code, write your own code, and it'll just exist on the internet in the dev account. So because the complexity is in a single repo and it's contained to the container, introducing really, really weird applications, like really weird stuff out there, doesn't make the ecosystem weird for everyone else. The ecosystem stays the same. Nobody on a different team, even knows that you have a really weird application that's running Go or Rust or whatever. There's no self-managed single point of failure. There's no build server that we manage. There's no deploy server. There's no managed load balancer that we have to bother with. It's trivial to add new environments. So when we decide that 4 accounts aren't enough, we can just say, okay, we're going to spin up a 5th account, and we're going to call that the Asian or the whatever. And that's where people from the Asian offices can deploy so that they have lower latency, and we're going to put that in a different region, or also because everything is contained in a single repo for one application. If you do a pull request, we can deploy that pull request and see the changes live, but not just like, hey, someone changed the string. You can change how the application is configured. You can change everything from configuration, the size of its containers, everything, because it's all in one repo. One pull request can change everything. Like I said, see pull requests live before merge. So if you have a QA team, a testing team that actually clicks through your application, if you have automated tests that require spinning up a browser and clicking around your front-end application, you can see all of that before, you can see and play with it before you merge. Trivial auto-scaling, it's literally a number. You want to go from 10 to 100 to 1,000, it's just a number, press save, change the template, commit it, and it's limitless. As limitless as it gets. I don't know if someone finds out how far AWS ECS Fargate scales, let me know. I imagine it's a number that we cannot pronounce. Quickly, the hurdles. What are the problems with this? CloudFormation is extremely fragile initially. The environment is slightly hostile starting out, and it takes a lot of trial and error to get to a place where you're being somewhat productive, where someone asks me, can we do this? And I go, yes, I think I know how to do that. And even then I don't, but I feel like I do. First deploy failing is the most irritating thing on CloudFormation, because on CloudFormation, if you do a change and it fails, it'll roll back to the last sane state. If you're first deploying something and that fails, it ends up in a weird state where the only thing you can do to it is delete it. You can't ship it again. You have to delete it. It's annoying. I'm not going to even. Elastic Load Balancer rule priority. Because CloudFormation is newer than some of the really old things on Amazon, there's some really weird interactions. So Elastic Load Balancer rules require, they have to have a priority. The priority is a number. It has to be unique. So if you have 3 rules on a load balancer, they have to have numbers. The numbers don't have to be sequential, but they have to be numbers. And when you're deploying independent applications or instances of an application, none of them have a defined number. If you're deploying pull requests, you could have 100 pull requests against a single application. Each of them needs its own number. I ended up doing the stupidest thing ever, but it's still the smartest solution that I came up with, which is I wrote a lambda that gives out numbers for unique strings. So if you go, hey, A, it'll say 1. If you say A, it'll say 1 again. If you say B, you're going to get 2. At some point, that's going to break, but whatever. But the absolute biggest hurdle was Dockerizing legacy applications. I had no idea. I genuinely had no idea. I thought we would be done with this project by June. We're not even remotely done. The platform exists, but the applications do not, because, oh my God, the stuff we did in Jenkins, there should be like a war tribunal for that. The things that developers got away with when I wasn't looking, the things that I put in there when I don't know what I was doing, I wasn't thinking. But this would happen with any tech. So if you're thinking containers, and you should be thinking containers. If you're not doing containers, you should be thinking containers. If you're thinking containers, you're going to have this problem whether you go with Kubernetes or ECS or whatever else exists out there that I'm not going to name. But this has been an order of magnitude more work than anything else that I talked about today.